Hello everyone, welcome to the channel. I hope you all are doing great. So we were discussing about the previous year questions of the CSIR NET exam, and in that the unit we have started was the kinetics, right? So already three of the parts of this unit we have discussed on the channel. So where some of the questions we discussed. So if you have not watched playlist I have made on the channel, you can check that, or I'll provide the link in the description. Even from that you can get the access to it. So now this is gonna be the part number 4 in this. So let us begin with this one. So these are the questions from the CSIR June exam conducted in the year 2019. Before this, the years which was from 2011 to 2018. Each and every single question has been discussed in the part number 3. Okay, so let us begin with this one. The question it says that if the half-life of a reaction it is inversely proportional to the square of the concentration of the reactant, what is the order of the reaction? So we know that for the nth order of a reaction, T half value, this is equal to 2 raised to the power of n minus 1 minus of 1 upon the n minus of 1 into the k into a naught raised to the power of n minus 1. So from here we are getting is that my T half value, it is inversely proportional to the initial concentration raised to the power of n minus 1. So here it's given that my T half, it is inversely proportional to the square of the concentration, or we can say this implies T half was inversely proportional to a naught raised to the power of n minus of 1, which means n minus 1 it is equal to 2. So n value it is equal to 1 plus of 2, which is equal to the 3. So this reaction it is corresponding to the third order kinetics. The answer becomes the option D in this case. Okay. Next is this question. The gaseous phase decomposition of A at 1000 Kelvin shows the two decomposition paths. A is giving us B plus C and A is giving us P plus Q. So this is from your parallel reactions, that is through the different paths you are getting the two different paths for the reaction, A giving us P plus C and A giving us P plus Q. So two different pathways have been followed. The rate constant for them it is given as 3-second inverse, and this is with the 5-second inverse. This is the rate constant K1 and this is the rate constant K2. So the maximum theoretical percentage yield of P is being asked at this temperature. So P we can say it is formed with the rate constant K2. So percentage of P, this will be equal to the final rate with which it is formed upon the rate constant sum that you are having, K1 plus K2 into the 100. This will be equal to 5 upon the 5 plus of 3 into the 100. So this becomes 500 upon the 8. So on solving this, the value we are getting it as 62.5%. So the correct answer is the option A in this case. Right? So now moving upon to the next one. So the next question we are having is this one. It says the photochemistry of a molecule M. It is described by the mechanism. So the various processes taking place in it are shown. That the molecule M, by observing the h nu energy, this is becoming the excited molecule. The rate constant for this is given as I observed, which means the rate expression for this it is gonna be I observed, right? Next is this excited molecule, by transferring its energy to the Q molecule, this becomes M plus the Q. The rate expression for this it will be KQ into the Q. It is KQ into the Q into the M star of it. Right? Now in the final step it is given that M star, it is coming back to the ground state with the emission of the H nu F, that is having the rate is this much, which is 0.2 into the M star of it. This is what is shown. So what are these processes basically? If from your Jablonski diagram you see, this is the ground state S0 and this is the S1. So here the molecule, suppose you are having, which is this M molecule. So this molecule M, it is observing some h nu amount of energy, and by observing this energy it goes to the excited state and it becomes the M star, right? So for this process the rate is given, which is the I observed. Absorption is taking. Then this M star, it is coming in contact with some other molecule Q and giving us the M and the Q, giving us M and the Q. So this process that is taking place, this is called as quenching of this process. This is called the quenching, right? So rate for this is also shown. And in the third step, this M star, it is coming back from the excited state to the ground state with the emission of the h nu f energy, right? And this emission is between the same states with some light, so radiative process is taking place, and this is called as the fluorescence. Fluorescence, it is taking place in this, right? So for this also, this rate expression has been given. Now the question, it says the intercept at q is equal to 0 is 4 for the inverse of fluorescence intensity, that is 1 by if versus the q plot, the value of the I observed will be. So the fluorescence process, it is taking place in the third step. So for that, the intensity of this fluorescence, it will be equal to zero point 0.2 into the M star of it, right? So now this M star that I am having, this is the intermediate. It is your intermediate. You have to eliminate this. So for this, we need is to find the concentration of this M star by using the SSA over here. SSA on the M star, we can apply it. For this, d by dt of this M star has to be kept equal to the 0, right? So now this value we have to find it. So the various reactions taking place is M plus the h nu, it is giving us the M star. So d by dt of this M star, this will be equal to the I observed, right? In the next process, which is M star plus the q, giving us the M plus the q. For this, minus of d by dt of the M star, this will be equal to kq times the q into the M star of it, right? And in the third step, which is the M star, giving us the M plus the h nu f. For this, minus of d by dt of this M star, this will be equal to the zero point 0.2 into the M star of it, right? So you can combine all of this and get the value of d by dt of the M star. So d by dt of my M star, this is becoming the I observed minus of the kq times the q into the M star of it, and minus of the 0 point 0.2 times the M star of it. This is equal to the 0, right? So from here we get that the I observed, it is equal to kq times the q into the M star of it, right? Plus of the 0 point 0.2 times the M star of it. From here, this M star value, it is gonna be equal to I observed upon the kq times the q plus of the 0 point 0.2 of it. This is the value of the I observe, this M star we are getting. So from here, the IF, which was equal to 0 point 0.2 times the M star of it, this substitution of this M star we can make over here. It comes out to be as I observed upon the KQ into the Q plus of the 0 point 0.2. This is equal to the IF. Now the plot we want is for the inverse of this fluorescence intensity, which means the 1 by IF value. 1 by the IF, this will be equal to 1 by IF is KQ times the Q upon the 0 point 0.2 into the I observed of it plus of the 0 point 0.2 upon the 0 point 0.2 into the I observed of it. So this is being cancelled out. It becomes KQ times the Q upon the 0.2 into the I observed plus of the 1 by I observed of it. So 1 by the IF, right? So here it is 1 by IF versus the Q plot. So Y is equal to the MX plus of the C. So the Y intercept that you are getting, it is 1 by I observed. 1 by I observed, and its value it is given to us that the intercept at Q is equal to 0, which means that the X value they are keeping it to be the 0. At that point the intercept which we get it is called as the Y intercept. Its value is given to us as 4. So that means 1 by the I observed, it is equal to the zero point 0.4, it is equal to the 4. So from here the I observed value, it is 1 by 4, which is equal to the 0.25. So this is gonna be the I observed value, and this was what I were asking, the value of the I observed, which is 0.25. Option B, it becomes the correct answer. Okay, so I hope all of this is clear. Now moving upon to the next one. So this begins the questions from the December exam conducted in the year 2019. Okay, so the first question, it says, if the rate constant for a base catalyzed ester hydrolysis reaction, it is this much, the half-life of this ester, we have to find it out. So here the rate constant units, if you see, it is mole inverse liter per second. So this corresponds to the fact that the reaction is of the second order, right? Because it has the rate constants units as mole inverse liter per second of it. Now for the second order, the integrated rate expression we have is 1 by A minus of the 1 by A naught. This is equal to the KT of it. So at T half, A value, this is equal to the A naught by the 2. So it becomes 2 by the A naught minus of the 1 by A naught. This is equal to the KT half of it. So it becomes 1 by the A naught into the K, which is equal to the T half value, right? So just substitute the values now. T half will be equal to initial concentration, which is 0.05 mole per liter, and the K value, which is 0.20. So on solving this, the value we will be getting it as, so this becomes 100 and this also the 100. So 5 and to the 20 it becomes the 100. So this value and this 100 gets cancelled out. So the time we will be getting it as 100 seconds. So the T half for this, it is 100 seconds. Answer is the B in this case. Okay. Next one is this question. The rate constants for a second order reaction, which is 2A giving you the Z, is K2. If the initial concentration of the reactant is A naught and the concentration of the product at time t is equal to x, then the linear function of the t with the slope K2 A naught is okay. So for the second order reaction, which is shown as 2A to the Z, it is showing the rate for it is K2 times the A square, you will be having it. Initial concentration, so this is the reaction to A to the Z. Initial concentration of it is given as A naught. This is at time t is equal to 0. This formed will be negligible, and then after the time t, this is at t is equal to 0. After some time span of the t, this has the remaining concentration as A naught minus of x, and this is the x which has been formed over here. For this reaction, the integrated expression we have is 1 by A minus of the 1 by A naught. This is equal to K2 times the t of it. Now the A's value, it is equal to A naught minus of x, and the A naught capital, it is your small a naught. This is equal to the K2 times the time t, right? So this becomes A naught minus of the A naught minus of the x upon the A naught into the A naught minus of the x. This is equal to the K2 times the time t. So this A naught and A naught gets cancelled out. It becomes x upon the A naught minus of x. It will be equal to K2 times the A naught into the T. This A naught I am taking it on the other side. So the value we are getting it as x upon the A naught minus of x. This is equal to K2 times the A naught into the T of it. So what is they were asking, that the slope value is this much, K2 times the A naught. So this becomes, if you make a plot, y is equal to this mx, that is versus the time, this value versus the time, the slope value we are getting it as this one. So the linear function of the t, it is gonna be x upon the A naught minus of the x versus the time plot it is being there, right? So the y value we have got it as x upon the A naught minus of x. Option C, it becomes the correct answer for this one. Okay, I hope it's clear that they are asking the concentration of the product is this much, then a linear function of the t with the slope. It means that t is taken on the x-axis. So this is what we have taken over here. Okay. Next one is this question. The oxidation of the NO to the NO2, it takes place through this mechanism. The d by dt of the NO2 in the presence of the large excess of the oxygen, it will be written as. Okay. So we will be applying the SSA conditions that you can find the concentration of d by dt of the NO2. So here this NO2, it is getting being formed in the final reaction. So from here we can write 1 by 2 times. So this reaction we are having, which is N2O2 plus the O2 with the rate constant K2. This is giving us 2NO2. So from here we will be writing the rate as 1 by 2 d by dt of the NO2. This is equal to the K2 times the N2O2 into the O2 of it, right? So now this N2O2, you can see it is formed in the one of the reactions, that is the first one, consumed in the second one. So this N2O2, this is your intermediate. This is your intermediate. And the final rate expressions, it can never be in terms of the intermediates. We have to eliminate it. So for that we make use of the approximations, that is the steady state approximation on this N2O2 we have to apply it. That means d by dt of this N2O2, this will be equal to the 0, right? So now to find this, the reactions is 2NO is in equilibrium with the N2O2. This is with the rate constant K1. This is with the rate constant K inverse. So we can split this. So I'm taking it in the above direction. So it will become 2NO, giving us the N2O2 with the rate constant K1. This is happening. So 1 by this d by dt of the N2O2, this will be equal to K1 times the NO square, right? And in the second reaction, which is N2O2, giving us the 2NO. This is with the rate constant K inverse. For this one, minus of d by dt of the N2O2, this will be equal to K2 times K inverse times the N2O2, right? So this is the another one, and the third expression in which the N2O2 is included, that is N2O2 plus the O2, is giving us the 2NO2. This is with the rate constant K2. So here minus of d by dt of the N2O2, this will be equal to K2 times the N2O2 into the O2. This is what we are getting. So in all these expressions where we have got this d by dt of the N2O2 values, this we can combine it and equate it to the 0, right? So d by dt of the N2O2, this will be equal to, the first one it was K1 times the NO square, K1 times the NO square. minus of the K inverse of the N2O2 and minus of the K2 times the N2O2 into the O2. This whole it is equal to the 0. So from here K1 times the NO square upon the K inverse plus of the K2 times the O2, this is equal to the concentration of the N2O2. Right, so now it is given that we are having in the large excess of the oxygen, which means that my K2O, this is gonna be much greater than that of the K inverse, right? So from here the N2O2 concentration, this becomes equal to K1 times the NO square upon the K2 times the O2. This is what the value of the N2O2 it's gonna be there, right? So now in the final rate expression, that was for the d by dt of this NO2. So it was half of the d by dt of the NO2. This will be equal to K1 times the K1 into the NO square into the O2 into the K2 upon the K2 times the O2. This is what it is becoming. So K2 and K2 will get cancelled out. O2 and O2 will get cancelled out. So d by dt of the NO2, it will be equal to 2 times the K1 into the NO square of it. So this is gonna be the final rate expression for the formation of the NO2. So the answer becomes 2K1 NO square. So the option A, it becomes the correct answer for this. Okay, so now moving upon to our next question, which we are having is this one. So this is from your November 2020 exam. The question, it says a substance A, it is exposed to 600 nanometers and 100-watt light for 6626 seconds with 50% of the intensity of the light being observed. A decomposes according to this reaction. As a result of the irradiation, 0.2 moles of the B is produced. What is the quantum yield? So quantum yield, it is defined as amount of the reactant dissociated to that of the amount of the photons observed. Amount of the photons observed. So in the given reaction, which is A giving us the 2B. So here they are saying that 0.2 moles of the B has been formed, which means 2B formed is 0.2 moles of it. So this from the 1 mole, 2 moles of it is getting being formed, which means 0.2 moles will be formed from the zero point 0.1 mole of this A. So the amount of the reactant that is dissociating, amount of the reactant that is dissociating, it is 0.1 mole. So this value we are getting. Now to find the amount of the photons which has been observed, the amount of the photons observed, this is gonna be equal to energy which is observed to that of the energy of the 1 mole of the photons. 1 mole of the photons. This is what we are having, or we can say it is equal to the energy of the 1 Einstein. Energy of the 1 Einstein. This is the value. So E observed, it will be E observed. This you can, for the 1 mole we can generalize it and you can get the value as 12 upon the lambda, which is the wavelength in the centimeters. Okay. So this value you just have to substitute now the value of the energy observed. So here you see that they are passing a light which is of the 100 watt for this much time period. The product of these two will give you the value of the energy which is being observed. So it is 100 watt, means joule per second only, joule per second. The time is 6626, and one more condition it is given, that only 50% of the incident light is being observed. So that means E observed is overall 50% of this, right? Upon the 12, upon the wavelength, which is in the centimeters, that is 600 nanometers the wavelength it is given. So it will become 600 into 10 to the power of minus of 7. This is in the centimeters you are having the wavelength. Okay, so this thing, and the ratios of quantum yield, it will be 0.1 upon this energy observed and this value, which is 100 into 6626 into the 50 upon the 100 upon the 12 upon the wavelength, which is 600 into 10 to the power of minus of 7 of it. So here the values we will be getting it as, this will be equal to 10 raised to the power of minus of 7 into the 600 into the 331,300 upon the 12. This will give us the value of 1.6565. So the ratios of this, which we will be getting quantum yield, this will be equal to 0.1 upon the 1.6565. So overall this value, this you will be getting it as 1.6565. So 0.1 upon this gives the value of quantum yield as 0.060, that we can write it as 6 into 10 raised to the power of minus of 2. So this is gonna be the quantum yield. Okay, so the answer becomes 2 into 10 6 into 10 to the power of minus of 2. Option C, it becomes the correct answer in this case. Okay, so now moving upon to our next question, that is this one. So here it says the concentration of the compound C undergoing the decomposition as a function of time interval. So concentration values are given to us at different time intervals. So here it means the integrated rate law expression we will be using. Integrated rate law expression, that means for the different integrated equations for the different orders of reactions, using this data we will be seeing the values of the rate constants for a particular order. If the rate constant values, it comes out to be the constant, then the data is for that corresponding order of the reaction. What it means, suppose the concentration terms are given us as 1, 0.8, 0.67, 0.5 and the 0.4, right? Time period we are having it as 0, 1, 2, 4 and the 6. So here if I check it firstly for the zero order kinetics. So for the zero order, the integrated expression is A naught minus of A. This is equal to the KT. So here the data, if we use it, first is this one. This is the A naught value and this will be the remaining concentration A. So the initial one we are having is the 1 minus the remaining, which is 0.2. This is equal to the rate constant K. The time span is of the 1 minute, right? So from this one, the rate constant value, it is coming out to be as 0.2. Right, now if you take the other data, that is A naught is this one and 0.5, where the time span is of the 4 minutes. If this data we are using, in this case again A naught minus of A, it is equal to the KT 1 minus of the 0.5. This is equal to the 4 times the K value. So this comes out to be as 0.5 upon the 4 is gonna be the rate constant, that comes out to be as 0.125. So here for the zero order we are seeing that one time we are getting the rate constant as 0.2 and other time it is 0.125. So here we can say is rate constant value, it is not the constant, which means the given data is not for the zero order kinetics. Right, now after the zero order we check it for the second order kinetics. For the second order, the integrated expression is 1 by A minus the 1 by A naught. This is equal to the KT of it. So again the same data we can use it Firstly, the first two, that is 1 by the 0.8 minus of the 1 by 1. This is equal to the k into the 1 minutes. So from here the k value we will be getting it as, so the k value will be 0.25 for this one. It is gonna be 0.25. Now for the second data, if I check it again, the 1 by a minus of the 1 by a naught, this is equal to the kt. Now the remaining concentration is of 0.5 minus of 1 by 1. This is equal to k. Time span is of the 4 minutes. So this again becomes 1 by 4 as the rate constant, that is equal to the 0.25. 0.25. So this is the value. So we are seeing here that the rate constant k as 0.25 and here also it is 0.25, which means that the k value it is coming out to be the constant in this case, which means the reaction is coming to be of the second order kinetics. So the option C, it becomes the correct answer in this. Okay. So like this you have to solve on the basis of integrated rate law. Now next is this one. It says for a reaction raising the temperature from 200 to 300 Kelvin, it results in the increase of the rate constants by a factor of the 2. So the activation energy in kilojoules per mole it is closest to. So this is from the Arrhenius concept when two of the rate expressions are given. So ln of the K2 upon the K1, this is equal to EA upon the R into the 1 minus of T1 minus of the 1 by the T2 of it. Now this value of the rate constants, when the temperature we have increased it, its value it is given that it is increasing by a factor of 2. So K2 by K1 is 2. This EA we have to find it out. R value it will be 8.314 joule per mole per Kelvin into the temperature 1 by the 200 minus of the 1 by 300. This is the value. So on solving this, the activation energy value, we will be getting it as 3.44 in the kilojoule per mole, which is approximately equal to the 3.5 kilojoules per mole of it, which means the correct answer becomes the option B in this case, right? Now the next question we have is this one. The question it says the rate constant of a reaction is given is described by this one. The activation energy of the reaction it is closest to. So this is log of K. Arrhenius equation we have it. The Arrhenius equation it is rate constant K is equal to A into e raised to the power of minus of the EA by the RT. Natural log of K, this will be equal to natural log of A minus of the EA upon the RT. Now ln K it is 2.303 log of the K. This will be equal to 2.303 log of the A minus of the EA upon the RT. Right? So now log of K we wanted. So log of K, this will be equal to log of A minus of the EA upon the 2.303 into the RT. So now the given expression and this one we can compare it, this one and this. So from here on comparing we get it that log of A value, this is equal to 14.1 and the EA upon the 2.303 RT, this value it is equal to 10,000 upon the T, right? So with this T will get cancelled out. So EA it comes out to be as 2.303 into the R value, which is 8.314. This will bring the value in the joules per mole and this value which is 10 to the power of 4 of it. In the kilo you have to find it. So divided with the 1000 it becomes kilojoule per mole. So on solving this, The value of the activation energy, we will be getting it as, so EA value, you will be getting it as 191.4 kilojoules per mole of it. This is gonna be the answer. So that is given to us in the option A. Okay. Next is this question. So this is from the June exam conducted in the year 2021. So it states the rate of decomposition of a gas is 10 millimolar per second when 10% it is reacted, and it is 5 molar per second when 40% of it is reacted. The order of the reaction is, we know that rate expression according to the rate law, this is equal to K into the concentration raised to the power of n of it. So rate R1, we will be having, this value is 10 millimolar per second, and the R2, it is 5 millimolar per second of it, right? And this one we are having when it is 10% reacted, so the remaining concentration of it, that will be C1, it will be the 100 minus of 10, that is gonna be 90%, right? Next one, it is 40% reacted, 40% reacted, so the remaining one, that is concentration C2, it will be the 60%, right? So the rate R1, this is equal to K times the C1 raised to the power of n, and R2, this is equal to K into the C2 raised to the power of n of it, right? So ratios of these two, R1 by the R2, this will be equal to C1 by the C2 raised to the power of n of it. This implies R1, which is 10 millimolar per second, upon the 5 millimolar per second. This is equal to C1, that is 90%, upon the 60% raised to the power of n of it. So on solving, we get the value. This is 3 by 2, and this units will get cancelled out. This will become 2. So we are getting it that 2, it is equal to 1.5 raised to the power of n minus of the 1. So take the log on both the sides. It will become log of 2. This is equal to n minus, not the n minus 1, just the power of the n, right? N into the log of 1.5, right? So n value, it will be log of 2 upon the log of 1.5. So this is equal to the value as 1.71, which means the order is this one, right? So the correct answer becomes the option B in this case. Okay. Next one is this question. This is for the reaction cis to the trans. We are converting this complex. The equilibrium constant is this much. K1 is this much. The experiment, it is starting with the pure cis form. The time taken for the half of the equilibrium amount of the trans isomer to be formed. So T half, it is being found. We have to find it out. So this question is basically from your portion of the fast reactions. So this is from the fast reactions portion. For this, the time, that is relaxation time tau, this is equal to 1 by K1 plus of the K inverse, that is for the reverse reaction. Okay, so here it is, instead of the K1 they have written as K2, so it will be 1 by K1 plus of the K2 of it. Right, now here the half-life have been asked. The half-life, so the reaction is of the first order kinetics only, so this is gonna be 0.693 upon the K1 plus the K2 of it. Okay, so this is gonna be there. Now the K1 value, it's already given, and the K equilibrium, it is given to us as 0.16, which is defined as the ratio of the rate constant of the forward to that of the backward direction. So from here, K2 value, it's gonna be K1 by the 0.16, which is equal to, this is 3.3 into 10 raised to the power of minus of 4 upon 0.16. So this will give you the K2 value, and the half-life, this will be 0.693 upon the K1, which is 3.3 into 10 to the power of minus of 4 plus of the K2, which is 3.3 into 10 to the power of minus of 4 upon the 0.16. So just solve this and you will be finding your value of the T half, which is approximately, it will be 267 seconds we will be getting it. So the closest match to this time, it is the 290 seconds. So T half, it becomes the first one. So it was approximately close to the 290 second, right? So the option A, it becomes the correct answer in this case. Okay, I hope it's clear. This is the one. So this solution, it will give you not the 267, it will be 297. Okay, so this is close to the 290 seconds only. And one more equation is there for the fast reactions, that is delta x is equal to the delta x naught e raised to the power of minus of the k1 plus of the k inverse of the time t, where k1 is the rate constant for the forward and this is for the backward direction. This you remember it. And the half-life, since it is the first order, that we have used it over here, which is 0.693 upon the k, which is the observed one. So overall rate constant, you are getting it as this only. So which means the observed rate constant is k1 plus of the k inverse. So this thing you just remember it for the fast reactions. Okay, so this one we have used it. Now the next one is this question. So this is from your September exam conducted in the year 2022. Okay, so the question, it says A plus B with the equilibrium. This is A plus B with the rate constants as Ka, and this is Ka dash, giving us the intermediate I, and then this with the some another rate constant, which is the Kb, giving us the product P. So for this, activation energies have been given and we have to find the expression of the energy. So for that, we need is the overall rate expression. So the final step in which the product formation is taking place is this one with the rate constant Kb. So the rate, it will be equal to Kb times the intermediate I of it. Now I is the intermediate, its concentration we need to find it out. So we have to apply the SSA on the I so that we can find its concentration. For that, d by dt of this I, this is equal to the 0, right? So now here these equations we are having is A plus the B, giving us the I, rate constant Ka, Ka dash. So A plus B is giving us the I with the rate constant Ka, and I is giving us the A plus of the B. This is with the rate constant Ka dash, right? For this one, the I is being formed, di by the dt, it will be Ka times the A into the B, and for this one, minus of db time d by dt of the I, this will be equal to the Ka dash times the I, right? And the other reaction, I is giving you the product P with the rate constant K2. So minus of d by dt of the I, this is equal to K2 times the I, right? So combine all of this and d by dt value of the I, this will be equal to Ka times the A into the B, Ka times the A into the B, minus of the Ka dash times the I, and minus of the K2 times the I of it. This is equal to the 0. So from here, Ka times the A into the B, this is equal to the Ka dash plus of the Kb times the I, right? This is K, not the K2, this is Kb, right? So from here, the I value, it comes out to be as Ka times the A into the B upon the Ka dash plus of the Kb. So this is the what the I value we will be getting, right? So the overall rate expression, it becomes this value, which was Kb into the I. So just substitute, it will become Ka into the Kb into the I upon the Ka dash plus of the Kb. This is what we are getting. So now if you see the final energy expression that we are having, so here three terms are included. So here in the rate expression, if I impose certain condition, that is Ka Kb into the I upon the Ka dash plus of the Kb. If I consider that my Ka dash is greater than that of the Kb, in that case rate expression, it will be Ka into the Kb into the I upon the Ka dash. This is what we will be getting. The overall energy expression for this one, this will be equal to Ea plus of the Eb minus of the Ea dash. This is what we will be getting, Ea dash, right? And the other case that we have it from the condition, if we impose that Kb is greater than the Ka dash, in that case the rate value, it will become Ka into the Kb into the I upon the Kb of it. So this Kb and Kb gets cancelled out. In this case the rate will be equal to Ka times the I only, and overall energy term in this case, this is gonna be the equal to the Ea only. So from the options, if I see, three of the energy terms have to be included. So from the final rate expression, I can see is this is the one which can match with my options, and this won't be the scenario, right? So the from the options, with this time we have to proceed it. So it was Ea plus of the Eb minus of the Ea dash. That means the option second one is your correct answer, right? Because it was not much clear from the curves that have been plotted. So from this rate, in that the various conditions we can impose it. Okay. Now the next one we are having is this question. It says that for a zero order reaction, the initial concentration of the A is A naught. The time required to consume all the reactants, which means T 100% is being asked to us. So for the zero order, the integrated expressions we have is A naught minus of the A. This is equal to the KT. So now for the completion, it means all the reactants have converted into the product. So that means A value, which is the remaining concentration, it will be 0. So A naught, it will be equal to K T 100%, right? So T 100%, it comes out to be as A naught upon the K. So this is gonna be the value, right? So A naught upon the K, so the option second one, it becomes the correct answer, right? Next is this one. In a reaction between two of the ions, the rate constant is Kr when the ionic strength is 0.004 and the rate constant is Kr naught when the activity coefficient is unity. The ratios of the Kr to the Kr naught is this much. If the charges on one of the ion is +1, the charges on the other ion, it will be. So this is from our primary salt effect. Primary salt effect. So according to this, we have the value like log of the K, it will be equal to log of the K naught plus of the 2A times the ZA into the ZB, where ZA, ZB are the charges present on the ionic species into the root of the ionic strength. So here instead of the K, they are having the rate constant as Kr, so that you can use it, and this is Kr naught, right? So log of the K R minus of the log of the K naught, Kr naught, this is equal to 2A times the ZA into the ZB, ZA into the ZB into the root of ionic strength, which is given to us as 0.004 of it, right? So now here you are having, it will become log of the Kr upon the Kr naught. This is equal to 2 times the Debye-Huckel's constant value, it is 0.509. charges on one of the ion, it is plus of the one. On the other one, that is ZB, we have to find it out. This is into the root of 0.004 of it, right? So now this ratio, which is of the Kr upon the Kr naught, this is given to us as 0.884. This will be equal to, that is 1 into the ZB into the root of 0.004 of it. So ZB from here, it comes out to be as log of the 0.884 upon the root of the 0.004. So the value of the ZB, we will be getting it as minus of the 0.79. So this is gonna be the charges on the other ion. So the correct answer, it becomes the option 3 in this case. Okay. Moving upon to the next one. This question you are having. It says carbonic anhydrase whose concentration is this much. It catalyzes a hydration of the carbon dioxide in the red blood cells, which is at a pH value 7.1 and at 274 Kelvin. The rate of the reaction reaches its maximum value when varied with the substrate. According to this equation, the catalytic efficiency of the enzyme. So the catalytic efficiency, it means K2 by the Km value, we have to find it out. So eta is K2 upon the Km. This ratio we have to find it out. So this question is from your enzyme catalysis topic. This is from our enzyme catalysis. So for this particular process, the rate value we have it, it is R max into the S upon the Km plus of the S, right? So the given expression, if you see, instead of R, a V term is used for the rate 1 and it is 1 upon the V, which implies 1 upon the rate it is there, right? So 1 upon the R, this will be equal to Km upon the R max into the 1 by S plus of the 1 by the R max of it. This is what we will be getting. So now instead of the RV is used, it becomes 1 by V into the Km upon the R max or the V max, it will become, this will be V max into the 1 by S plus of the 1 by V max of it. This is what we are getting. So now here if you use this expression and the other one that is given to us, it is 1 by V, it is will be equal to 4 times the 1 plus of 10 by the S naught, right? So 1 by V, it is 4 plus of the 40 upon the S naught, right? So here if you compare these two, you have is, this is 1 by V, this one, and 40 upon the S naught means this value you are getting. So from here, Km upon the Vmax ratio, we are having it as 40 and 1 by the Vmax value, this is equal to the 4, right? So we need it is now the efficiency value. So for that, we are having this Km. Vmax is nothing, it is K2 times the E naught of it. This is equal to the 40 only, right? So eta value, which is K2 upon the Km, this is equal to 1 by the E naught into this 40, right? So now the initial concentration of the enzyme, it is already given to us, which is 2.5 into 10 to the power of minus of 9, 1 upon 2.5 into 10 to the power of minus of 9 into the 40. So this decimal, it gets removed. So 10 and 10, 25 fours are as 100. It will become 10 raised to the power of minus of 7. So that implies the efficiency value, it will be equal to 10 raised to the power of 7 of it. So the answer, it becomes the option third one in this case. Okay. Now moving upon to the next one. This is the question. So the predicted rate law using the steady state approximation for this particular reaction. So various steps have been given. Rate of the reaction will be dependent upon the slowest step of the reaction. It is dependent upon the slowest step of the reaction. Now here the slowest step of the reaction is this one. So in terms of that rate, it will be equal to K2 times the HI into the H2O2, right? So now here look for the intermediate that is formed in one of the steps and being consumed in the other, which is your HI. It is formed in the first one, consumed in the second one. So its concentration we have to find it out. This is your intermediate. So SSA on the HI, this will be equal to d by dt of this HI. It will be equal to the 0. So now this only we have to find it out. So from the given equations, which is H plus of the I negative, this is in equilibrium with the K1, K inverse of the HI. You can write this as H plus of the I negative with the rate constant K1. This is giving us the HI d by dt of the HI, because it is being formed in this case. This will be equal to K1 times the H positive into the I negative, right? In the second reaction, HI will be giving us the H positive plus the I negative. This is taking place with the rate constant K inverse. So minus of d by dt of this HI, this will be equal to K inverse of this HI, right? And in the third reaction, which is HI plus of the water, HI plus of the water, this is with the rate constant K2, sorry, not the water, H2O2 gives us the water plus the HOI. This is the reaction. Again HI is consumed, so d by dt of the HI, this will be equal to K2 times the HI into the H2O2, right? So combine all of this, which is for the d by dt of the HI. So we will be getting it as d by dt of the HI, this will be equal to K1 times the H plus into the I negative minus of the K inverse of the HI and the minus of the K2 times the HI into the H2O2. This is equal to the 0, right? So from here the HI concentration that we will be getting, it will be equal to K1 times the H positive into the I negative upon the K inverse plus of the K2 times the H2O2. This is what we are getting. So the final rate expression, which was K2 times the HI into the H2O2, in that we can substitute this expression. So rate it was K2 times the HI into the H2O2. So rate it becomes K2 times the HI concentration, which is K1 times the H positive into the I negative upon the K inverse plus of the K2 times the H2O2, this into the H2O2. So this is the expression for the rate we will be getting it. So check it into the options. This one, K1 into the K2 into H positive into the I negative into H2O2 upon the K inverse plus of the K2 times the H2O2, which means the option A, it becomes the correct answer. Okay. Now the next one is this question that says that the effective rate constant for a gaseous unimolecular reaction, which is A to P, it is following the Lindemann-Hensvold mechanism, are this and this at the concentration A when it is this much, and the another one it is also given the rate constant of the activation step. So for the unimolecular reaction, for the unimolecular reaction, the mechanism that we obey is A plus of the A. this is activated with the rate constant K1, giving us the A activated plus of the A, and with the rate constant K inverse it is being decomposed, that is going in the backward direction, and then this A star it is being converted to the product P. This is with the rate constant K2, right? So the activation step rate constant we have is that is K1, right? So this is the one. So when two of the conditions you are having, that you are having the rate constants at the two different conditions and the initial concentrations are also given to us. So in that case we use this expression that 1 upon the Ka, this is for the observed rate constants, minus of the Kb, this is for the Kb dash, which is the observed rate constant at the concentration V. This is equal to 1 by the K1, which is the rate constant for the activation step, into the 1 upon A, which is the initial concentration A, minus of the 1 by V, which is the initial concentration B when you are having it. So Ka dash, the first rate constant, we are having it as 1.70 into 10 raised to the power of minus of 3 minus of 1 upon the 2.20 into 10 raised to the power of minus of 4, which is the second rate constant. This is equal to 1 upon the K1 into the 1 upon the initial concentration. First time it is 4.37. Let me just do it on the next slide only, because we will be not able to write it completely and it will become hodgepodge over here. So we are having is 1 by the Ka dash minus of the 1 by Kb dash. This is the observed rate constants, which is equal to 1 by K1 into the 1 by A minus of the 1 by B of it, right? So here this value, which is 1.70 into the, this is 1.70 into 10 to the power of minus of 3 minus of the 1 upon 2.20 into 10 to the power of minus of the 4. This is equal to 1 upon the K1 into the 1 upon A1 value, we are having it as 4.37 into 10 to the power of minus of 4 minus of the 1 upon B's concentration is 1 into 10 raised to the power of minus of 5. So 1 into 10 to the power of minus of 5. So we just have to solve this and find the value of the K1 over here, right? So in this case, you will be getting the value as, this will be 588.2 minus of 4545. This is equal to 1 upon the K1 into the 2288.329 minus of 10 to the power of 5 of it. So this K1 value we get it as 24.69, that is approximately 24.7 only. So this is gonna be the rate constant for the activation step. So the answer given to us is in the option fourth one. So fourth becomes the correct answer in this case. Okay, so this was the last question that was to be discussed in this part. So I hope all the questions that I have discussed so far, be it in this part or the previous parts, these all are clear to you. If you still have doubted any of the questions, you can ask me in the comment section. I'll surely reply to that. And if you have understood the concepts, then make sure you hit the like button for the video, and don't forget to subscribe to the channel, because many more parts and many different chapters are on the way. So that is it, and make sure you share it with your friends as well. So thank you so much for watching. I'll be meeting you in the next video now with the next parts of this. Okay.